Today we shall talk about the Ampere's circuital law, very important to find out the magnetic field produced by a current carrying conductor, and it is a very simple way to find the magnetic field produced by a current carrying conductor. Now see, first of all, this is the law for a closed curve in a magnetic field. The line integration of magnetic field is equal to the product of permeability of vacuum and electric current enclosed by the curve. Okay, so it is nothing but, say for example, you have this current carrying conductors. Now try to understand this figure. These horizontal lines are current carrying conductor, and we have considered one closed loop, or we can say closed curve. Okay, so for a closed curve in magnetic field, line integration of magnetic field is equal to the product of permeability of vacuum and electric current enclosed by the curve. So curve is considered by you. This is a curve which you have considered. Now let me show you this in a different way. Okay, now see, this three ball pens which I have shown, pencil come ball pen, they are current carrying conductors. They can be anywhere. Try to understand. This current carrying conductor can be anywhere. It can be here also, wherever you want to place, you can place. And they are vertical, I have kept. In that it is shown horizontal. Whatever way they are lying, you can keep. Now you want to say find the magnetic field produced by these say three conductors, and you want to find it somewhere here at this point. So what you have to do, you can consider an Amperian loop which encloses this conductor. So this is the loop or a closed curve which has been mentioned in the law. You can take this closed curve. Closed curve generally we take whose length we can measure easily. Length means the perimeter. So here perimeter can be measured easily. So it's a circular closed curve which is enclosing these current carrying conductors. Okay, now here right hand rule is also considered. Now try to understand it this way. Okay, say for example, you have these three current carrying conductors. Okay, and this is the loop which has been talked about in the law. You have to consider a loop which encloses the current carrying conductor. That is the main thing. That loop you have to consider on your own. Okay, now you can see that there are three current carrying conductors. Now the current in them can be, say one is having current in this direction, the other one is having the current in this direction, third one is having the current in upward direction. Now the loop which you have considered is this loop. Now what you have to do, you have to curl your finger in the direction of the loop. So these are the fingers which are curled, you can see. Any way you can keep your thumb down, and you can keep you can curl your finger. Okay, you have this freedom. Again I am showing, say current which is, say for example I take the another color. This is the direction of electric current. One is going down, one is going up, this is going up, and this is the loop which we have considered. Okay, now you have curled your finger in this way. You can curl your finger in the other way also, then your thumb will be down. Okay, this is thumbs up. Okay, so now this is the direction in which you have taken your fingers which are curled. Okay, so your fingers are curled in this direction. The direction of the thumb is in upward direction. So whichever current which is in upward direction, now try to understand this. The current in this, say first, is in upward direction. current in this third conductor is in upward direction, second is in downward direction. So you have to take the currents which are there in the direction of your thumb. These currents are taken positive. These currents means the upward direction current are taken positive. And the current which is in the downward direction is taken negative. So say current in the first is I1, current in second is I2, and current in the third is I3. Then the algebraic sum of this current can be upward you are taking positive I1, downward you are taking negative, so I2, and the other one is also upward, so plus I3. So this is the algebraic sum of electric current. This is the algebraic sum of electric current. So the law which suggests us that you can have for a closed curve in magnetic field, the line integration of magnetic field is equal to the product of permeability of vacuum and electric current enclosed by the curve. Now these currents can be many. Here also there are many currents you can see in this. These are the different currents. 1, 2, 3, many currents are there. Then you have to take the algebraic sum of electric current. Here the currents are in same direction. So all the currents are taken and the value is say I. Okay, the value of this current which is enclosed by this loop. Okay, that loop is enclosing the current whose value is I. Okay, so the law has this mathematical equation that integration, see, this is a closed integration which is shown here. It is spoken as contour integration or closed integration B dot dl. See, the line integration of magnetic field. What is this? Line integration of magnetic field. So line integration of magnetic field is equal to the product of permeability, that is mu 0. Okay, product of permeability of vacuum and electric current enclosed by the curve. Say electric current enclosed by the curve is I. Okay, if currents are in, some are in this direction, some are in this direction, then you just have to curl your finger in any one direction and the direction of thumb will show the direction, will show the currents in the direction of thumb. Try to understand currents in the direction of thumb are taken positive and the other currents are taken to be negative, opposite to it. Okay, so integration, rather close integration B dot dl is equal to mu 0 I. This is a Ampere's circuital law, or it can be written in this way: close integration B dot dl is equal to mu 0 sigma I, where sigma I is the algebraic sum of electric currents. This we have to keep in mind, that the sigma I is the algebraic sum of electric current. Currents which are there in one direction are taken positive and current in the opposite direction are taken to be negative. Okay, this we have to keep in mind. Now in this law, a surface considered which has a boundary, okay, surface which we have considered as having a boundary, okay, the loop which we are considering, I is the algebraic sum of electric current passing through the boundary. How to take, I have explained. The integral is taken over the closed loop coinciding with the boundary C of the surface. So here this C point is nothing but the boundary point. Okay, so a curve is passing through this C point, we can say. Okay, and the closed integration is taken. Okay, the integral is taken over the closed loop coinciding with the boundary C of the surface. The relation above involves a sign convention that I have explained, given by right hand rule. Let the finger of the right hand be curled in the sense the boundary is traversed in the loop, that is B dot dl. Then the direction of the thumb gives the sense in which the current I is regarded as positive. So the direction of the current which is there in the direction of thumb, that current is taken positive. The other current is taken negative. That I have explained how to do it. Okay. Again I am showing it. Okay. Say for example you have this current in upward direction, this is in downward direction, and this is in upward direction. Then this is our loop. Say for example this is our loop. Here some point C is there, which is there on the boundary point, or we can say this is the closed loop which is having a boundary. You are curling your finger in one particular direction, then thumb is in this direction. The currents which are there in the direction of thumb, they are taken positive. So this is positive, this is positive, this is negative. So I showed you that two currents are positive. If you take this as I1, I2 and I3, then it can be written as I1 minus I2 plus I3, that is algebraic sum of electric current. Okay. Now we have say possibilities to choose the loop called Amperian loop. The loop which we have considered, okay, this yellow colored loop which is shown here, okay, this particular loop is a closed loop. Now this closed loop, how can we choose, or how the loops are chosen? Okay, it is very easy to choose the loop. Possibilities to choose the loop called Amperian loop. B is tangential to the loop and is non-zero constant. Okay, or B is normal to the loop. You are choosing the loop in such a way that the magnetic field is tangential to the loop, or B is normal to the loop. Direction of magnetic field is normal to the loop. Now it is shown here. See, if you consider only one conductor right now, this, okay, then this is the current carrying loop. Okay. Now if you want to find the magnetic field at this point, then say for example this is your position according to Biot-Savart's law. I am trying to explain. This is vector r of this point P. You consider a very small current element. See, this is your current element, that is IDL. Now you have to take IDL cross R. If you are rotating this IDL in the direction of R, then the vector which is rotated, that is in this direction, and vector R is in this direction. So if you are rotating IDL, that is DL, in the direction of R, then the direction of magnetic field at this point will be tangential coming out of the screen. Try to understand, it will be coming out of the screen. Okay, so it is tangential to this particular loop. So you have chosen the loop in such a way that the direction of magnetic field is tangential to the loop. Generally we choose the loop in this particular way. So this is a guideline to choose the loop, how to choose the loop. Okay. So B is tangential to the loop and is non-zero constant B, or B is normal to the loop. This way also you can choose the loop. Sometimes you choose the loop in such a way that B vanishes, or the resultant value of B becomes 0. Now let L be the length, that is part of the loop for which B is tangential. Let IE be the current enclosed by the loop. Then equation 1 which we had, what was the equation 1? Equation 1 was closed integration B dl is equal to mu 0 into I. Now the length of the loop is what? L. So if you take the integration of dl, means all the dl if you consider, say for example this is the loop, this is the current, small dl are added, then we will have the length of the loop, and length of the loop is taken as L. Then dl results into L. So B into L is equal to, you will have mu 0 I, and if the current which is enclosed is shown by IE, then this can be written as mu 0 L is this can be written as BL is equal to mu 0 IE. Again I can explain it with this figure. Say for example the length of this loop which we have considered, yellow colored loop, this orange color loop is, say length of this loop is L, and our equation is what? Integration B dl, okay, close integration B dl is equal to mu 0 I. Now the magnetic field produced is in this direction, coming out of the plane or tangential. Okay, here this magnetic field B and length dl, see length dl and magnetic field B, both are in same direction. I have tried to explain that magnetic field is in this direction and the curve you are taking in this direction, so both are in same direction, both the vectors are in same direction. This dl is in the direction which is coming out, and the magnetic field both are in same direction, so this dot product result in B dl cos 0, so it becomes B into dl. Now if you consider this small dl, all this dl if you take, then it will give you the length of the loop, and it is shown by L. So we are taking as B into L is equal to mu 0 current enclosed, whatever is the current enclosed is denoted by IE. So BL is equal to mu 0 IE can also be written as a different form of this ampere circuital law. Okay, so it is written as BL is equal to mu 0 IE. You have to take what is L, try to understand. L is nothing but the length of the loop. Try to understand length of the loop. Say here one current is flowing and you have enclosed it with a particular loop. That loop you can take, that loop you have to choose in such a way that the magnetic field is to be found somewhere here. Then that loop has to pass through it. So loop you have chosen. So now you can write B into L is equal to mu 0 IE. IE is the current which is enclosed by this loop. Okay, you have your fingers curled in this direction, then the thumb is showing the direction upward. So upward currents are taken positive, downward currents are taken negative, and resultant current is IE. I is the resultant current. Whatever currents are there, one is in downward direction, the third one is in upward direction, fourth one is also upward direction. Then 1, 2, 3 currents are added. This fourth current is subtracted. Then whatever is the result is the current IE. That is algebraic sum of electric current. Okay. So it is very easy as such. Ampere circuital law is used to determine when there is a system with a symmetry. Okay, as Gauss law was used to find electric field. This law is applicable for steady currents. Current should not change every now and then. There must be a steady current passing through the conductors. Now, magnetic field of infinitely long current carrying wire. Okay, this is a long current carrying wire. This has been magnified. Okay, this is a cylinder, but the wire is having a cylindrical shape. Now, this is the loop which we have considered. This is Amperian loop. Say for example, I want to find out the magnetic field somewhere here at this point P. Okay, so I have passed a circular loop through this point P. Okay, So this is very easy. See, there was no loop earlier. This is a current carrying conductor. Okay, current is flowing. Say for example, current is in this direction. Then I consider a loop. Okay, this is the loop, and loop is passing through the point say P where I want to find out the magnetic field, and this is a circular loop. Okay, now the wire is having the radius R, and this red colored, you can see this red colored is a radius of the loop. This red colored part is a radius of the loop, and the point P where we want to find the magnetic field is here. Okay, so you have chosen this Amperian loop which is passing through the point P where you want to find magnetic field, and the radius of this Amperian loop is R. Okay, so this radius is R. Now the radius which is shown by this black colored line, that radius is of the wire. Okay, wire is having the radius A. Okay, radius of the wire is equal to A, and radius of the circular loop is R. This is the point where we want to find out magnetic field. Okay, and the next is the axis of this wire. You can see this axis is passing through the center of the wire. Okay, now consider a wire of infinite length. This is an infinitely long current carrying conductor. The wire is cylindrical in shape, that you can understand. The radius of wire is A, that is that black colored which I have shown you. Okay, so here this is the wire, radius of wire or black colored part, and this orange colored part is radius of the circular loop, Amperian loop. Okay, we want to calculate magnetic field at point P. Now where is point P? That also I have mentioned. Okay, this is the point P, or we can say it is shown by this dot. Okay, say this dot I am showing, there is there the point P is located. Okay, which is a distance, this distance shown by orange color. Okay, shown by R. Okay, or red color line, and here R is, you can see R is greater than A. Okay, now consider an Amperian loop of radius R, which we have considered already, such a way that the center of the current carrying wire is at the center of Amperian loop. Length of the loop, as it is circular, its length will be 2 pi R. Okay, and current enclosed by this is I, that is current which is passing through the cylindrical loop. Say for example, this is the loop, and current passing through it is I. This is your axis of the current carrying conductor, and this is the loop. Here we want to find the magnetic field, and the distance of this is R. So radius of this loop is R, therefore its length will be 2 pi R. What current does it enclose? It encloses current I. Okay, so it is very easy now. We have the equation integration V dot dl is equal to mu 0 I E whatever. Then B dl if you consider, then the length of this loop will be 2 pi R. Okay, is equal to mu 0 whatever current is enclosed, that is I. So B is equal to mu 0 I upon 2 pi R you will get. Okay, so according to Ampere's circuital law, B into L is 2 pi R is equal to mu 0 I. So B is equal to mu 0 I upon 2 pi R. So the current carrying conductor of infinite length is producing the magnetic field of value mu 0 I upon 2 pi R at this point. Okay, so we can consider it this way, that if you have this current carrying conductor, and if you want to find the magnetic field at distance R, then its value here is mu 0 I upon 2 pi r. Okay, so the direction, the value of magnetic field is mu 0 I upon 2 pi r. It is an infinitely long current carrying conductor. It is having finite value of magnetic field. If you have infinitely long current carrying conductor carrying current I, then it does not produce infinite value of magnetic field at this point. Okay, it has a finite value. From above result magnetic field produced by infinitely long current carrying conductor, we can conclude that the field at every point on the circle of radius r is of same magnitude if the distance is kept same. Okay, say you have a circle, then magnetic field at all these points, this point, all the points, okay, the magnetic field will be same at all these points which are there on this circular current carrying loop. Okay, the field direction at any point on this is tangential to it. Now try to understand this way. If you want to find the direction of magnetic field, okay, then you just have to consider the right hand thumb rule again. Now see, you just have to take, this is your current carrying conductor. Okay, now hold this conductor in your hand in such a way that thumb remains in the direction of electric current. So this is the direction of current. So thumb will be in this direction and fingers are curled around it. So this is the direction of the thumb, which is there in the direction of electric current I. Now if you try to understand that your fingers are curled like this, okay, because your thumb has to remain in upward direction, so fingers are curled in this direction. So if you consider the point here, then the magnetic field would be coming out, that is in the direction of the finger, that is coming out of the screen. If you want to find the magnetic field here, then your fingers are going inside because fingers are curled in this way. Okay, this way you have curled the finger. So at this point, the magnetic field is going inside. Okay, so this way you can find the magnetic field by using the right hand thumb rule. Even though the wire is infinite, the field due to it at a non-zero distance is not infinite. The field is directly proportional to the current and inversely proportional to the distance. What is the formula for the magnetic field? B is equal to mu 0 I upon 2 pi r. So B is directly proportional to current. More the current in the wire, value of magnetic field will be high, and if you have more distance from the current carrying conductor, if you are away from the current carrying conductor, then the magnetic field will be low. More the distance, less the value of magnetic field. Okay, there exists a simple rule to determine the direction of the magnetic field due to long wire. This rule called the right hand rule or right hand thumb rule. Grasp the wire in your hand, that is right hand, with your extended thumb pointing in the direction of the current. So what I explained, that your thumb should remain in the direction of electric current. Your fingers will curl around in the direction of the magnetic field. So the direction of magnetic field is in the direction in which your fingers are curled. Okay, thank you very much.